Discuss this example of norm again. See, this time we have a set L2. Let us try to understand what is meaning of L2. L2 is that means infinite sequences are there. Okay, if you consider element of L2, it will look like this: x1, x2, and so on, xn. Okay. See, infinite elements are there such that the series is convergent, less than infinity. That means the always infinite sum is having a finite value. So this is a convergent series. Okay. So see, what we have to prove, we have to prove that it is a non-linear space. Non-linear space, that means it should satisfy how many conditions? 4 conditions. First one is that norm should be greater than or equal to 0. Second, it is equal to 0 if and only if x is equal to 0. Third, alpha is there, you can take it outside with the but when you take it outside there should be mod. And yeah, and the last condition, if you take a separate norm, okay, the value will get increased. Okay, so these properties we have to prove. So let us start to prove the first property. So for that we have to take one element. Okay, so let I am taking one element. X is equal to x1, x2 and c. Xn dot belongs to L2. Okay, it is just like a Rn, but in Rn there are finite number of elements, n number of elements, but here we have an infinite number of you can say elements or coordinates. See, x is equal to this one I have considered. Okay, and norm 2. See, norm 2 is defined in this way. Raised to 1 by 2 means raised to 1 by 2 means square root summation n running from 1 to infinity xn square. Okay, so this is the definition of norm 2. So clearly we can write clearly xn square is greater than or equal to 0. This is true for all n. Since you know that when you take square of any real number, obviously it is non-negative, it is always greater than or equal to 0, and this is true for each n. So that means if you take a sum of all these numbers, then also it is greater than or equal to 0. So therefore summation n running from 1 to infinity xn square is also greater than or equal to 0. So after that I am going to take a positive square root. So let us take its positive square root. So square root of summation n running from 1 to infinity xn square is also greater than or equal to 0. But this is definition of norm 2. So therefore norm x2 is greater than or equal to 0, and this is true for each x belongs to L2. So in this way we prove the first property. Okay, so let us try to prove the second property. So in second property we consider norm 2 is equal to 0, and after that we will try to prove that x is equal to 0. See, so consider norm x2 is equal to 0. See, if and only if. So let us apply its definition. What is the definition? So its definition is square root of summation n running from 1 to infinity xn square is equal to 0. So see, you know that what I am going to do, I am going to take a square of both sides. So if you take square of both sides, we will have summation n running from 1 to infinity xn square is equal to 0. See, we are taking sum of all these elements, then also we are getting 0. That means each term should be 0. So that's why if and only if xn square is 0, and this is true for each n belongs to set of natural number. See, square is 0, that means no original element should be 0. So that means xn is equal to 0. This is true for each n belongs to set of natural number. So that means our x will be, so x is actually x1, x2 and so on, xn and so on, but all of them are 0. So that means x will be 0, 0, 0, 0, 0, all entries will be 0. So if and only if, simply we can write our x is, simply in simple language we can say x is 0. We started with norm x2 is 0, and finally we got x is equal to 0. So in this way we proved second property. Okay, make a screenshot of it, and after that we'll go for a third property. See, in third property what we do? In third property we take one alpha and we take alpha outside. Okay, and when it comes outside, it should be, there should be mod. Okay, so let us try to prove. So this is equal to norm alpha. X means simply we can write x1, x2 and so on, xn and so on. Okay, norm 2. So this is equal to norm. So see, what will I do? Yeah, obviously when you multiply alpha, we have to multiply each component by alpha. So therefore we will have, this is alpha x1, alpha x2 and so on alpha xn and so on norm 2. Okay, so now we are ready to use the definition of norm 2. What is the definition of norm 2? Yes, it is clearly mentioned here. Okay, so because of that, this definition I can write, see, raised to 1 by 2 means square, raised to 1 by 2 means square root summation n running from 1 to infinity alpha xn square. Okay, since this here we have simply xn, but here we have alpha x1, alpha x2, so I suppose to write alpha xn square. So this is equal to square root of summation n running from 1 to infinity. If you take square, multiplication is there, that's why we can take separate square, alpha square xn square. See what will happen, alpha square is independent on n, so it will come outside the summation. Okay, so yeah, square root of alpha square summation xn square n running from 1 to infinity. Okay, see, we can take separate square root. When you take a separate square root, see, this alpha has a square root will get cancelled to each other, so therefore, but positive square, so that's why I am taking mod alpha square root of summation xn square n running from 1 to infinity. So you know that this is the definition of what? Norm x2. So mod alpha norm x2. Okay, so we started with norm alpha x and finally we proved mod alpha norm x. Okay, so in this way we proved the third property. Make a screenshot of it. After that we go for the last property. Okay, so let us continue. So in fourth property we require two elements. So I have taken two elements, and what we have to prove? We have to prove that norm x plus y less than or equal to norm x plus norm y. This thing we have to prove, right? So we have to make them separate. If you make them separate, value will get increased. This thing we have to prove. Okay, so let us start. Okay, but it is not that much simple how much we are thinking. So see, what will I do? First of all, I am going to use Minkowski's inequality. So when you have a norm 2, okay, most of the times we take the help of Minkowski's inequality. So see, by Minkowski's inequality, see, already we have used this inequality, I think, in a previous example. So that equality, this inequality says summation I running from 1 to n xi plus yi square and raised to 1 by 2 is less than or equal to summation xi square I running from 1 to n raised to 1 by 2 plus summation I running from 1 to n yi square raised to 1 by 2. This is Minkowski's inequality. See, but this is true for finite summation. Here we have an infinite summation. We have an infinite summation. So that's why we cannot directly use this Minkowski's inequality. So first of all, I have written for a finite terms. Okay. So after that, what can I do? Okay, see what I'm going to do in the next step. So therefore, summation I running from 1 to n xi plus yi square raised to 1 by 2 less than or equal to summation I running from 1 to n xi square raised to 1 by 2 plus summation I running from 1 to n yi square raised to 1 by 2. So now you will think that I have copied this same step. Okay, nothing is different there. So see, different thing I am going to write here. So this is less than or equal to, summation I running from 1 to infinity xi square raised to 1 by 2 plus summation I running from 1 to infinity yi square raised to 1 by 2. So that means the difference is, if you take, here we had a finite number of terms, right? So when you take infinite number of terms, so that means we will have a more value. So this is less than or equal to this one. Understood now what is the difference? Here we have n terms, here we have infinite terms. So that's why value became increased. Okay, so see, therefore summation I running from 1 to n xi plus yi square raised to 1 by 2. So you know that a less than b, b less than c. So we can write a less than c, same thing. Okay, but see, this is nothing but this is the definition of norm x2. So therefore this is norm x2 and this is definition of norm y2. So that's why we got this one. Okay, so this part is less than or equal to this one, and this is true for each n belongs to set of natural number. Okay, I will write it here. See, it is less than or equal to this one, and this is true for each n. That means if you at a place of n, if you take n plus 1, it is okay. For n plus 2, it is okay. N plus 3, it is okay. N plus n, then also it is okay. That means for each n it is true. So that's why we can go up to infinity. Then also this inequality will hold. So therefore, summation I running from 1 to infinity xi plus yi square raised to 1 by 2 less than or equal to norm x2 plus norm y2. See, this is true for each n, no? So that's why that means here simply I applied the limit and I wrote there infinity. Then also it is true. But this is a definition of, this is definition. Same definition we have got square raised to 1 by 2. So this is the definition of norm x plus y2. Getting since xi plus y. Here simply we have xi. But here we have xi plus y. So norm x plus y2 less than or equal to norm x2 plus norm y2. Getting now? So therefore, yeah. So therefore, in this way we prove the last property also. That means this norm 2. Okay, it satisfies all 4 properties. So that's why we can declare it is a norm on L2. So therefore, norm 2 is norm on L2. So therefore, L2 norm 2 is norm linear space. This is short form of it. So it is a norm linear space. Okay. So the problem is over. You can make a screenshot of it and after that we'll stop. Thank you.